In this video we're going to do the multiplication algorithm and the division algorithm. Now we've already covered the multiplication algorithm in the first CPU design course. So if you're not interested in that and you've done it before, then I suggest if you don't want to listen, just skip ahead 10 minutes and get to the division algorithm. I've just put this in case there's people out there who haven't actually completed the first course and have gone straight to the second course. So let's look and see how we multiply 5 times 5. So in binary, this is going to be given by 101. So we can put that in register 1, and we've got 101. Again, we can put that in register 0. So in order to multiply these two together, what we can do is we can look at the least significant bit here of R0. Now if this least significant bit happens to be a 1, then we know that all we do is multiply the 1 with all of this. So we're just left with this R1. So what we can do is we could take the contents of R1 and just read it into another register, say R0. So we could R2. So we could add R1 with R2. So we'd just be adding 0, 0, 0, or 8 zeros with the top line here, and we'll get this value here. Okay. So what we could do then is we could shift this value R1 to the left. So in effect, when we shift this to the left, we're multiplying it by 2, or we're going up by a significant bit. So it's equivalent to shifting this here in by 1 factor. And then we can go through the same process again. We can check and see whether the value is a 1. If it's a 1, again we just add the value on to the contents of register R2. If it's a 0, then we don't add anything on. All we do is we just shift again to the left onto the next significant bit up, and we continue working around that process until we're completed, and we should get the final answer here, which in this case here will be the value 11001. Now, difficult to explain in words, and we'll see if we can work our way through it, and it might become more apparent what's happening. So let's have a work through the actual code. So here's the code here. The first line here loads the value 5 into register R0. The second line loads the value of 5 into register R1. And the third line here adds the value 1 into register R3. Now we're going to use register R3 as a little counter, because it's going to be working through a loop, and it'll work through 8 times. So originally R3 starts off with a value of 1, and then it works its way up the significant bits until it gets to the very end. And when it's at the very end, we know we've went through the code 8 times, and then it'll jump out of the loop. Okay, so that's just for counting purposes. Now we begin here and we exclusive OR R2 with R2. So when you exclusive OR the two numbers are the same, you get a value of 0. So it's just a way of initializing this register and setting it to 0. We then clear all the flags, and then we go on to line 5. Now this shift right is really the start of our loop, and it's the start of our code, proper code. Okay, so we go in here and we shift the value on register R0 to the right, and then we jump if the carry is set. So we can see here, if we go back to this line here, we're going in here and we're shifting this to the right. So in this instance here, when we shift that to the right, this value of 1 is going to drop out, so the carry is going to be set. So to convince yourself of that, you can go in and have a look at the ALU, and you'll see when you shift right with this value 1, the carry flag will be set. So it means that if the carry flag is set, then the next line says jump carry, so it'll jump to this line here. Now this line here is 1, 2, 4, 8, so that's line 13. Now you have to be careful here, because that 13 isn't line 13 here, it's actually memory location 13. So the memory locations that you're actually going to go to, well, remember here the date instruction contains 2 bytes, okay? So that's going to be memory location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it jumps to the clear flag instruction. And then the next line is add the value register R1 into R2. So you can see here that in this instance here, when we're multiplying these two numbers together, we've checked that this is a 1. It is a 1. In that case, whenever you multiply the 1 with all of this, you're just left with the value of R1. So you can take the value of register R1 and you can add it to the value of register R2. So originally R2 started off with all zeros, so when you add R1 to R2, you just get this number here, which is the number 5. Okay, so we've got down to this point here. It clears the flags again. It goes in and it shifts left the value of R1 and puts it in R1. So that's taking this thing here and shifting it left. So when you shift this number here left, in effect you're multiplying it by 2. So it's equivalent to working through the shift left here whenever you do the normal multiplication. So if we've shifted this left, what we can do, the last thing to do now is we shift the value of R3 to the left. So originally the value of R3 has just got a value of 1, and we shift it 1 to the left, so now it goes to this point here. And then we've got to go and check and see if the carry has been set. So if this had actually been all the way along to point 8, then the carry would be set whenever we shifted left, and we'd know we'd be at the end of the program. And if we were at the end of the program, we would just go on to the next line here, which would be the jump. Well, it would be a jump carry, so we'd be jumping to the very end here, and that would be the end of the program. But that's not the case here. We've only got to a value of the next most significant bit up. So in that case here, it's not a carry, it's no carry there, so it just goes to this point here. And this point says jump to this line here. So this line here is 1, 2, 4, so that's 4, 5, 6, 7. So it's going to go to line 7. So line 7 again, it's going to be 0, 1, 2, 3, 4, 5, 6 and 7. So the 7th line is a clear flag, and then it starts over again. So this is the next part of our cycle here. So it takes the register R0 and again it shifts it to the right. So when we have a look at R0 here, R0 this time is going to have the value 0 at that point. So when it gets shifted to the right, it's going to shift out a 0. So if we get down here again and it's shifted out a 0, now we know the carry's not going to be set now whenever it shifts out that 0. So it's jump if carry to that line, so that doesn't occur. So what happens is it goes on to the next line and it actually jumps now to this point here. So this point here is going to be 1, 2, 4, 8, 12. So this point here is actually just one beyond the add instruction, because we don't need to add anything on here because it's just a value of 0. So it's just it just jumps to this line here and it clears the flag, and then again it shifts the value on register R1 to the left. So it shifts this here again to the left. So shifting to the left again, it's like multiplying by 2. It's equivalent to moving along here in our most significant bits whenever you do the normal multiplication. So we get to that point there and we add on 1 onto register R3 again, and when we add the 1 onto register R3, we're now on at this point here. Okay, so we're shifting it left and we're at this point here. We're still not finished yet. We're not finished, so it jumps back again to the clear flag instruction, and it continues again with the shift right for R0. Now we work our way through this until eventually our R3 gets to the most significant bit here, and when it drops off right there, there's a carry here and it says jump carry to the end, and it gets to the end of the program. Now it's a bit of a mouthful and it's a bit dull listening to that. The best way to do it is for you to work through it yourself. And if you set up the registers, so we say register R0, R1, R2 and R3, you put in the initial values and then you work through the values on the register as you work through each of the cycles here, okay, each of the loops, and you'll see the registers changing, and eventually you'll see the final answer will be in register R2, which will be this 11001, which is 5 times 5, which is 25. So, and finally we can see here that the actual code for the program is written down here. Okay, so this is in machine code, and you can see the amount of instructions. There's going to be 23 instructions, so it's 22 plus a 0, so it's 23 instructions. So there's 23 1 byte, there's 23 bytes in this program, and this is on the right hand side, this is actually written in hex. Okay, so this is the hex code that we go and we'll load into the CPU. So the last 10 minutes covering the multiplication algorithm should have been a bit of revision if you've already done the previous course. So if you go ahead and open up the assembler debugger, you can see that we have a copy of that in one of the pages here. So if you head to sample programs, and you'll see up here, the second one in here, we've got an unsigned multiply shift, so you can always copy that and paste it in to the assembler here, and you can change the two numbers here to 5 and 5, and if you assemble and you can debug and run that, and you'll see that you get the answer 25. And you see it runs through every value, and this is the value 25 here. So you see there's a lot of redundancy here because it actually gets to the answer 25 away back here, but it continues on with the algorithm. But we'll talk about that, the redundancies in these algorithms, in a later video. So let's move on to the division algorithm. Let's consider that we want to divide 14 by 3. So we can say that 14 divided by 3 is going to give us a value of 4, and the remainder will be 2. So we can say that the 3 here is the divisor, the 4 is the quotient, and the remainder is 2. So you might be more used to seeing it in this format here. We say 3 into 14, well it goes 4, and we do 4 times 3 is 12, and we subtract those off, we'll get a remainder here of 2. So in this lies the simple little algorithm we're going to use for division. So we're just going to be using a repeated subtraction. So we're going to look at it and we'll say 14 minus 3, and then we're going to take 3 away again, and so on and so forth. But the test is going to come here. We're going to have to test if the divisor, that is this number here, so the 3, is greater than the remainder. So if the divisor here is still greater than the remainder, it means we can still go through and do another subtraction. But if it's not greater than it, then it must either be equal to or less than. So if it is equal to it, it means that we'll have done a clean division and there won't be any remainder. Or if it's less than, it means that we're going to have a remainder. For example, in this example here, we're going to have the remainder 2. So we're going to have to work through this little algorithm. So let's go ahead and we'll do that now in the assembler debugger. So head into the resources section and open up the assembler debugger. You can press clear just to get back to a clean sheet. Now if you head into the sheet called sample programs, you'll see the third one in here is called unsigned division. So you can see it divides R1 with R0 and puts the answer into R1. So we can copy this here and just paste it in. So this here is our little algorithm, so we're going to talk through this. So we start off by putting our two numbers into the registers R1 and R0. So we put 14 into R1 and we put the value of 3 into R0. Now the compare and then the jump if A is greater is the test to see whether the divisor is greater than the remainder, and if it is, we head off to the end of the program where we output our values. So we'll leave that for the moment and move on to the next line. So if it isn't greater than, then it means that we can subtract off another value of 3 from the 14. But in order to subtract them off, we're going to have to add on the 2's complement. So to add on the 2's complement, we have to have a number 1 in R2, and then we have to naught the value of R0. And once we've naughted the value, we can add the value R1 on to the naughted value, and then finally we can add the 2's complement value back on to the value in R1, and we maintain that value in R1. So in effect it's taken 14 minus 3 and it's put it into R1, and then we go back to the line 2, so that's going to be line 0, 1, 2, and we work through the process again, and it checks to see whether the value R0 and R1, it compares them, and again we're comparing the divisor with the remainder, and it works through this and it continues to work through this until eventually the divisor is either less than or equal to the remainder, in which case it jumps to this line here. So this line is actually line 19, so that's 1, 2, 4, 8, 16, so line 19. So line 19 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, line 19. So at this point here we just do some tidying up. We put the quotient into R1 and the remainder goes into R0, and that's what these lines here do. So let's go ahead and we'll see that working. So you click on Assemble and Debug, and I'll press Escape just to run through it a little bit quicker, and you can see it counting down 14, 11, 8, 5 and then 2, and at the very end here you can see here that the quotient, which is a value of 4, sits in R1, and the remainder, which is a value of 2, sits in R0. So that's us able to add, subtract, multiply and divide, but it's very limited because we can only add and subtract numbers from -128 to 255, and we can multiply and divide only positive numbers between the values of 0 and 255. So what we want to be able to do is extend and expand on that, and we will get onto that in a later section whenever we cover the number systems and we work on a floating point unit. But there is a reason why we wanted to go through the simple add and subtract, multiply and divide here at this early stage, and that's because we want to try and look at some of the CPU and algorithm metrics. That is, we want to be able to see how long our algorithm takes to run and how efficient our algorithms are. So we'll go on to that in the next video, and then in the next section we'll continue and we'll expand on the assembler, and we'll make it look more like a modern assembler, and we'll make it much easier to write our assembly language code. So thank you for listening to this video. I'll get you on the next video. Goodbye.